Details of a new particle accelerator that is twice as deep and 3 times larger are being revealed today by the European Centre for Particle Research, or CERN. It has found 3 new particles that may provide insight into the origins of our universe and its prospects. Recent discoveries made by CERN scientists completely alter our conception of the cosmos, a world of particles and forces so strange they could be taken directly from science fiction exists beneath the surface of their ground-breaking studies. What enigmatic secrets lie beneath these experiments, from particles that threaten the very basis of reality to possible portals to other dimensions? Let's explore CERN and discover the mysteries that might reshape the cosmos. Because of the pioneering research carried out at CERN, the location of the Large Hadron Collider, LHC, a wormhole might hypothetically materialize out of nowhere in the sky. The LHC, the biggest and most potent particle accelerator in the world, is situated close to Geneva, which is where France and Switzerland meet. There are mysteries surrounding this odd organization that the public is unaware of, mysteries that might alter our understanding of the universe's mechanics. This enormous scientific device is run by the European Organization for Nuclear Research, or CERN. It is located deep down and spans more than 27 kilometers. The Large Hadron Collider's main purpose is to enable physicists to test the predictions of many particle physics theories. This includes the well-known study of particle physics standard model, which enables us to comprehend the basic components of the cosmos. Fundamentally, the Large Hadron Collider accelerates protons to almost the speed of light before colliding them. Scientists examine the shower of new particles created by these collisions to learn more about the principles of nature. In 2012, the Higgs boson, also known as the God particle, was discovered thanks to these investigations. This finding was crucial to particle physics and helped validate how particles acquire mass. Understanding phenomena that take place in extreme environments, such those immediately following the Big Bang, depends on the experiments carried out at the Large Hadron Collider. We can learn more about the fundamental components of matter and the origins and evolution of the universe from the data gathered. Because of this, the Large Hadron Collider may play a role in revealing new dimensions of reality, dimensions that may help solve puzzles related to dark matter and the basic laws of existence. There are some worries about such cutting-edge experimentation at CERN. Some people think that high-energy experiments might produce weird stuff or black holes that could endanger Earth. Nonetheless, the scientific community keeps a careful eye on these experiments, and CERN makes sure that all safety precautions are taken. Risky circumstances are extremely uncommon, according to studies and theoretical models. Through its continuous investigations and findings, CERN advances our understanding of the cosmos and shows the amazing power of human creativity and teamwork in the quest for knowledge. The CERN's Large Hadron Collider is a marvel of contemporary science and engineering, not just a remarkable technological achievement. The massive collider, which is located beneath the Swiss-French border, travels through a tunnel that is 27 kilometers in diameter and up to 175 meters deep. This makes it one of the most important tools in particle physics and the biggest particle collider in the world. The Large Hadron Collider's construction is built to support experiments of previously unheard of magnitude. 2 nearby parallel beam pipes are part of the collider's primary ring, which is contained within a 3.8-meter diameter tunnel. Protons are accelerated by a sequence of superconducting magnets and directed in opposing directions by each pipe. These magnets are essential for keeping the protons on course and bending their trajectory at nearly light-speed velocities. In order to keep the superconducting magnets at the correct operating temperature, layers of cooling systems that keep the temperature below space surround the beam pipes. The utilization of thousands of magnets, including 132 dipole magnets to bend the beams and 392 quadrupole magnets to focus them, further emphasizes the size of the Large Hadron Collider. The enormous physical scale and technological ambition behind the Large Hadron Collider are demonstrated by the use of the largest and most potent superconducting magnets, which are 15 meters long and 35 tons each. The Large Hadron Collider's main goal is to see the smallest particles of matter in order to investigate the fundamentals of the universe. The Large Hadron Collider enables physicists to investigate the particles created during collisions by speeding particles to almost the speed of light and then colliding them. The standard model of particle physics, which currently provides the best explanation of the subatomic world, is tested and our comprehension of it is expanded through this process. Solving the Higgs boson's riddles is one of the main goals of the experiments conducted at the Large Hadron Collider. Its 2012 finding at CERN supported hypotheses on particle mass gain. In order to answer important problems like the existence of dark matter and the nature of the cosmos soon after the Big Bang, the Large Hadron Collider also studies other fundamental particles and forces. The Large Hadron Collider also aims to confirm the existence of novel particles that have not yet been detected but are predicted by theoretical physics. The possibility of finding novel physics beyond the standard model, such as supersymmetry and dimensions other than the well-known three spatial dimensions, depends on these experiments. With hundreds of experts from more than 100 nations collaborating, the Large Hadron Collider aims to promote global cooperation in addition to understanding the fundamentals of the cosmos. One example of international collaboration in the pursuit of knowledge is the Large Hadron Collider. The magnitude and design of the Large Hadron Collider allow it to address some of the most important physics problems. Its goals go beyond simple scientific curiosity. They include expanding our knowledge of the cosmos and encouraging international scientific cooperation. Humanity is continuing to push the limits of knowledge and explore the quantum realm with this massive and complex device. The Large Hadron Collider, which is at the center of CERN's research facilities, acts as a potent microscope into the quantum world, enabling researchers to see and examine the fundamental particles that comprise the cosmos. One important technique for examining the fundamentals of physics is the acceleration and collision of particles at the Large Hadron Collider. Two beams of high-energy particles move through the collider at almost the speed of light before colliding. These beams replicate the conditions of space flight by passing through tubes maintained at extremely high vacuum. The beams are guided and focused at specific collision places along the tunnel by superconducting electromagnets that have been chilled to temperatures lower than space. Particles are smashed together with tremendous energy as these beams contact. Numerous subatomic particles are created by the collisions, some of which are extremely unstable and only last for a few seconds. The Large Hadron Collider is outfitted with huge detectors EAS, CMS, ALIC, and LHCb, each of which is intended for a particular type of research to identify and examine the byproducts of these collisions. The mass, charge, and momentum of the particles are among the information that these detectors record. Scientists use this data to investigate particles and forces that govern the universe and test predictions of particle physics models, such as the Standard Model. The 2012 discovery of the Higgs boson was one of the most important results from the Large Hadron Collider. This particle, which is sometimes called the God particle, is important because it supports the Higgs field, which gives elementary particles their mass. The Standard Model predicted that the Higgs boson would exist, and its finding was a huge accomplishment that validated long-held theoretical predictions. The Large Hadron Collider has played a key role in the discovery of a variety of additional particles in addition to the Higgs boson. For example, the collider has proven the presence of tetraquarks, which are particles composed of 4 and 5 quarks, respectively, and offered evidence for the existence of pentaq. Our knowledge of hadronic matter, matter composed of quarks held together by the strong force which holds atoms' nuclei together, is widened by these discoveries. These results demonstrate the Standard Model's predictive ability and pave the way for new particle physics research directions by shedding light on how matter behaves in harsh environments, such as those immediately following the Big Bang. Theories concerning the possible dangers of the Large Hadron Collider are growing along with its capabilities. The formation of strangelets and the possibility of producing miniature black holes are two of the most talked about theoretical risks connected to the Large Hadron Collider. Both the general public and scientists have expressed interest in these possibilities. Theoretically, strangelets are a more stable kind of matter than regular matter. According to the theory, strangelets have the ability to change whatever material they come into touch with into weird matter. There is concern that this idea may lead to a catastrophic chain reaction that would turn all matter on Earth into weird matter if strangelets were created during particle collisions at the Large Hadron Collider. However, these worries have been allayed by CERN's and the international scientific community's thorough investigations and safety evaluations. According to research, if strangelets were created at the Large Hadron Collider and were real, they would probably be extremely unstable and decay too fast to alter the substance of the Earth. Furthermore, The Earth is frequently hit by cosmic rays, which are high-energy particles from space, with energies significantly greater than those generated by the Large Hadron Collider. But no strangelets are created. According to this natural experiment, strangelets are not a real danger. Theories of extra dimensions in physics give rise to the hypothesis that miniature black holes could be produced by the Large Hadron Collider, LHC. High-energy collisions inside the LHC could create small black holes that would dissipate relatively immediately as a result of a phenomenon called Hawking radiation, which is named after physicist Stephen Hawking, according to certain theoretical models. According to experts, mini black holes would not be dangerous if they were ever produced at the LHC. Any such black holes would, first of all, be extremely tiny and fleeting, vanishing before they could interact with the stuff around them. Second, even though the energies involved in LHC collisions are enormous by human standards, they are still far less than those of naturally occurring cosmic ray collisions. It is extremely improbable that the LHC would have any negative impacts because no destructive tiny black holes have been seen from cosmic ray interactions. To make sure that the experiments carried out at the LHC do not endanger people or the environment, CERN and independent committees carry out thorough safety reviews. To address any possible dangers, these reviews take into account experimental evidence, theoretical research, and safety regulations. Even though the LHC's experiments are still pushing the limits of our knowledge of physics, they are carried out under strict scientific supervision and with a great deal of care. This guarantees that innovative discoveries will benefit humanity without posing an excessive danger. The theoretical risks frequently resemble science fiction rather than realistic scientific findings. Based on thorough investigation and natural cosmic occurrences, scientists generally agree that the activities at the Large Hadron Collider are safe and pose little dangers. The search for magnetic monopoles is one of the most interesting and unusual experiments that have been proposed at CERN. A hypothetical particle that is a magnet with just one magnetic pole, either the north or south pole, is called a magnetic monopole. Ordinary magnets, on the other hand, always have a north and a south pole. Paul Dirac, a scientist, predicted the existence of magnetic monopoles in 1931 and showed that their presence would account for the quantization of electric charge, which only occurs in discrete amounts. Magnetic monopoles have never been seen at the Large Hadron Collider, despite their theoretical significance. Evidence of these elusive particles has been sought after by researchers. Magnetic monopoles, if discovered, would fundamentally alter our knowledge of magnetic fields and potentially result in important technological breakthroughs, such as the creation of novel energy transmission and storage systems. Furthermore, grand unified theories and string theories, which aim to explain all of nature's fundamental forces within a single framework, would receive experimental support from the discovery of magnetic monopoles. Despite its arcane appearance, the hunt for magnetic monopoles is a prime example of the spirit of inquiry and discovery that propels scientific research at CERN. The Institute's dedication to exploring the unknown and pushing the boundaries of human knowledge is reflected in its search for such uncommon and potentially revolutionary particles. Examining the possibility of particles traveling faster than light is the subject of another unique experiment at the Large Hadron Collider. The speed of light is the universe's ultimate speed limit, according to Einstein's theory of relativity. The existence of particles known as tachyons, which would always travel faster than light, is suggested by several theoretical theories. The discovery of tachyons would radically alter our conception of causality and space-time. The search for tachyons at the Large Hadron Collider is evidence of the facility's willingness to investigate even the most speculative facets of theoretical physics. Despite the fact that the majority of scientists are dubious of their existence, scientists can also perform experiments at the Large Hadron Collider that replicate the circumstances of the early universe right after the Big Bang. Quark-gluon plasma, a state of matter created by these high-energy collisions, was present only a few microseconds after the Big Bang. Physicists are hoping to learn more about how the universe changed from its original high-energy state to the intricate and well-organized universe we see today by examining this plasma. Essentially, these non-traditional experiments at CERN, which range from producing quark-gluon plasma to looking for magnetic monopoles, highlight the scope and aspirations of the scientific work carried out in the Large Hadron Collider. They demonstrate the ways in which CERN is expanding our understanding of the cosmos and investigating previously uncharted experimental physics. By smashing particles at previously unheard-of energy, the Large Hadron Collider seeks to advance human understanding and solve the universe's riddles. It enables researchers to investigate the underlying characteristics of matter and the forces that govern the cosmos. Humanity's natural curiosity and drive to explore are reflected in this unrelenting quest to understand the unknown. Our understanding of the universe is profoundly affected by the discoveries discovered at the Large Hadron Collider. These investigations help us better comprehend the universe's beginnings, development, and ultimate destiny by examining the tiniest constituents of matter and the underlying forces at work. They assist answer some of the most important questions about life and provide insights into the very fabric of reality. Furthermore, the scientific and technological developments brought about by the Large Hadron Collider research have real-world uses outside of particle physics. Advances in a number of disciplines, including information technology, material science, and medicine, have been facilitated by the creation of sophisticated detectors, computer systems, and data analysis methods. Additionally, the Large Hadron Collider investigations stimulate a new generation of scientists and promote worldwide collaboration. To discover the secrets of the cosmos, researchers from all around the world collaborate and exchange knowledge. This international collaboration is evidence of how science can bridge divides and unite people in the quest for knowledge. To sum up, the Large Hadron Collider is a vital component of contemporary physics, facilitating ground-breaking discoveries and expanding our understanding of the cosmos. Its experiments shed light on the nature of fundamental particles, forces, and matter's beginnings, offering crucial answers to life's mysteries. The Large Hadron Collider is a prime example of the spirit of scientific investigation and the boundless possibilities of human curiosity thanks to its technological advancements and multinational partnerships. We get closer to addressing some of the most important concerns concerning our universe and our role in it as we continue to investigate the cosmos using the Large Hadron Collider.